Hello, everyone. It's my great pleasure to present our latest work on Ethereum scaling, how to achieve 10 GigaGas per second EVM execution with block-level access list. So a quick intro of myself. My name is Chi. I've been working in this space for about 8 years. Before that, I was a PhD and also engineer at Facebook, Google. I'm particularly interested in Ethereum infrastructure, especially scaling, and received a couple of support from Ethereum Foundation, including Vitalik personal grant. So why we want to do this work? So we know that Ethereum aims to scale dramatically by increasing the gas limit of Ethereum L1. So the current goal is to target for 100x gas increase so that we can achieve about 5 gigagas per block. So which means that in order to validate the blocks in about 4 seconds in the consensus time budget, we will require at least about 1.6 gigagas per second of the execution throughput. However, this creates a concern that whether we are able to handle this performance using current client, especially based on our commodity PC to ensure decentralization. So here is the number that these days we can get that now gas can only offer about 300 million gas per second, and also RAS is a little bit higher, close to 600, but still far from our target. So why the scaling is so difficult? The main reason is that there are a couple of the limits imposed, which both in terms of the disk I/O and also CPU execution latency. So here is one of my favorite diagram, which is generated by Flashbot a couple of years ago. So this shows that the disk I/O OP codes like S-load and core OP codes takes about 70% of the execution time without any optimization, like for example pre-warming or optimistic execution. So, and then block level access list basically remove this bottleneck from disk I/O to CPU execution. So Tony gave a really excellent introduction of the block level access list. So if you want to learn more, I will encourage you to watch his presentation yesterday. So basic idea is to include what the transaction in the block will access, including its account and also storage, smart contract, so that when we begin executing the transaction, we are able to preload all this data in parallel so that we can fully utilize the disk I/O. So on the right-hand side is a diagram shows the number of throughput versus the number of parallel I/Os, where we can show that right now our disk can easily support more than 32 I/Os concurrently, so that we can easily achieve about 30x performance improvement in terms of disk I/O, so that now we can remove those random disk access to latency now to the current sequential execution. So with all these ideas, now we are trying to study how BAL can also improve the parallelization in terms of CPU execution. So here is our setup. We are running all these experiments on top of Ethereum mainnet blocks so that we can get some real numbers. And we are also running on top of AMD 16-core CPUs, so which takes about 100 euro per month to rent this machine. And also we are experimenting, so simplify the whole experiment so that everybody can easily reproduce our numbers. For example, all the state has been preloaded so that we don't need to worry about corresponding I/O cost. And we also recover all the senders, which is very CPU intensive, but it's not related to EVM execution. And lastly, we do not include the state root computation, which can be amortized by the large blocks that Ethereum is growing. So the first number we get is to just run all this execution sequentially without any I/O costs. And so this is the number that we can fully utilize a single CPU, 100% utilization, and the number we can get, which achieve about 1.2 gigagas per second. And then by increasing multiple threads so that we can run corresponding transaction in parallel within a block, we found some interesting number. So we found when we increase the number of threads, we see some performance improvement, but it quickly capped at about 4 times for performance. That is about 5 gigagas per second. The reason is that we found there are some of the transactions that can be hardly be optimized by parallelization. So there's a famous called Ammendahl's law, which tells that even though we are able to increase the throughput by parallelizing all these transactions, however, the whole execution time will be limited by the longest transaction that can be hardly be parallelized. So here is the famous equation that we can see this number called 1 minus time optimized. That is the part that accounting for the longest transaction. So in the Ethereum mainnet, we also do the experiment where we found that even we are able to increase the number of the threads to improve the total time, but the longest time the transaction execution latency just keeps constant, and which result in 4 times performance cap in terms of the parallelization of threads. So how we are able to solve this problem, the basic idea is how we are able to break the granularity so that we can have smaller granularity by 2 directions. One is to improve the block size, block limit, gas limit, which is Ethereum is currently doing. And second thing is to limit each transaction gas limit so that the ratio between these two will be small, and which means that we are able to increase the parallelization even with multiple threads, like 32 threads. And so this gives us really encouraging numbers whereby we merging the mainnet 50 blocks, try to simulate the mainnet execution, but after that, for example, 50 or 100 gas limit increase by merging these blocks so that we are scheduling all this parallelization among these 50 blocks rather than single block, which we can show almost linear scaling in terms of number of threads. And the final number that we can achieve is about 40 gigagas per second, which means that we are able to achieve not only 100x, but almost 1,000x of performance improvement by increasing the gas limit of Ethereum. That is really, really encouraging number. Also, we do some study on how to, for example, changing the size of the mega blocks from 1 to the 200. And we found that right now 50 mega block is the sweet point, which is pretty fit to the current Ethereum scaling plan to increase 100x block size block gas limit. And so these numbers are really encouraging, but we're still facing a couple of engineering challenges if we really want to put these numbers into the production. So here I will list a couple of the challenges we found during our experiments. The first one is the called standard recovery. We found that the standard recovery is significantly underpriced. So even we are able to fully, for example, computing all this standard recovery, but accounting all this recovery computation speed, it just the performance significantly reduced to about 5 gigagas per second, which means that we need a better way to solve the standard recovery, either increase the gas or either we are able to using other more powerful computation devices like GPU. And there's also other things like, for example, we do not consider IOs because all the data has already preloaded into the memory. But actually the IO will also, even we are able to do it in parallel, but still maybe takes considerable time. And also the BAL itself can take significant overhead in the block size. So we need advanced algorithms, for example, P2P algorithms or EPBS, and also PDAS can also help to propagate those BAL information with, for example, pipeline execution so that we are able to fully utilize BAL without worry about the propagation latency. And another thing is like the BAL here is more experiment for the validators, but there's also limits from the builders how it's able to build this BAL quickly. So this is right now a really open questions. Maybe the idea is using super powerful builders and then using all in-memory database, all these kind of techniques. But still, a lot of what's the performance limit here is still an open question and probably with our future research work. And lastly, is about how we are able to compute the state rule. For this direction, I feel a bit more optimistic because we are able to amortize the cost with larger block gas limit. So here I give some quick result of how we are able to reduce the BAL size with the parallel I/O considerations. So the basic idea is that actually we have different types of BALs. With the larger size of BAL may contain more information. For example, it may contain information of the not only the location that we are going to read, but also corresponding value. And also, we have to include the post-transaction diffs so that we are able to schedule the transaction execution early. So here we summarize 3 types of the BALs, and we show that the parallel I/O BAL, which only includes the post-transaction diffs, will reduce the corresponding BAL size to about 1/3 with the most expensive full BAL, which contains all the information, I/O information during the execution. And so we try to understand, suppose we want to reduce the BAL size, for example, to 1/3, what is the performance difference there? And our result shows that by reducing the BAL size, we are able to still achieve some pretty good numbers, especially I think that the number that should be enough for our midterm or midterm requirements on the user transactions. So it's about like achieve 10 gigagas per second, which is about 6 times of the even 100x of current Ethereum gas limit. So here is the summary of today's talk with BAL, and by increasing the gas limit of Ethereum by also imposing the per transaction gas limit, we are able to significantly improve EVM throughput with more than 10x or even more, as demonstrated by our experiments. Also, we found there are some limitations during this study, like how we are able to improve the sender recovery, maybe using GPU or by repricing, or how we are able to reduce the BAL size by using different types of BAL strategy. And also how we are able to impose the per transaction gas limit by EIP 7825 so that we are able to easily optimize for our performance target. So that's all the talk I have today. So I would love to answer any questions you have. Thank you very much.
You mentioned Amdahl's law that the block is always, the execution time is always constrained by the longest transaction.
Yes.
But is that like keeping in mind that that single transaction is executing sequentially, or can you actually parallelize like the transactions themselves, where like maybe certain function calls, especially if they're like pure, you can actually parallelize them within the execution of the transaction itself?
Yeah, that's a really great question. So it is regarding what is the granularity parallelization that we can achieve. So definitely there's the idea that we are able to, even within the transaction, we can split the transaction and have some intermediate state of each transaction and tell how we are able to early execute the transaction in the middle state in the same time, and now we are able to run those get further gains. But this requires significant modification of current BAL standard, because the BAL standard is more designed for the per transaction, tells which transaction, what kind of state you have changed, or what kind of state you want to access. So definitely there can be a future work so that we are able to say, hey, this is really super long, maybe a single transaction take over all the block execution, and then we want to split them so that we are able to fully utilize the parallelization. But I think, yeah, there can be a lot of work can be done in the future research.
Is it on? Now it is. Great talk, very clear as well. So you talked about increasing the gas limit. I was wondering if there's some effect of block size here. As you increase the block size, you're going to increase your communication network overheads. Is that something that's relevant, or does it nowhere near being the bottleneck?
So the question is, when we are, for example, increasing 100x block size, will that become the bottleneck of the, for example, P2P network, right? Is that right? Yeah, so actually there are a couple of other solutions that are proposing to address this problem. So I have some kind of like my end game to address this problem. So first of all, we have kind of ePPS. There's an excellent talk by Terence yesterday, tells how we are able to pipeline the corresponding the consensus, so that now we are able to not only just require 4 seconds timing budget, but much longer time, maybe 12 seconds timing budget to broadcast the block, and then execute this transaction in the next block. So kind of a pipeline execution, so that we are able to increase the corresponding time budget. But this just brings about 3x gain, so it's still far away from 100x. So there are a couple of ideas, like for example PADAS, so that now we are able to also pack BAL and also block. I mean the block itself, not just the. So the block will be encoded in the block. There's a idea proposed by Vitalik saying that in the future all the blocks will be encoded in the blobs, so that we are able to significantly increase to, I think target is 32 megabytes per block in the future, or maybe even more. And so with that idea, so that together with pipeline execution, because propagating and sampling is just guarantee the data is available, and it's not guarantee and be able to validate the transaction. So with pipeline transaction, that tells that I can delay verify those transactions in the previous couple of blocks, so that I can still able to obtain a large number of the block data with the much longer latency, of course, and be able to verify the transaction execution of the block is correct, and then do the corresponding vote. So there are a couple of ideas flying around to address this idea. But definitely they worth a lot of research work to make it happen. Any other questions? I think, okay. Yeah, maybe one more question, see if. Okay, then thanks everybody. If you have any more questions, feel free to reach out to me, and I'd love to see how we're able to make the Ethereum the world computer. Thank you.